Okay, this is a simulation of the motions of the sun and the moon in the sky. Here the yellow dot represents the sun and the white dot represents the moon. And the Earth in this simulation is a flat disk and the sky is a sphere. This is the apparent view of the Earth and sky if you just walked outside and looked up. It's also the view of the universe that was taken literally by all ancient cultures. We know today that these bodies in the sky are at very different distances, and yet they all appear to be projected onto this sphere. The sun, for instance, is 400 times farther away than the moon, and yet they both appear the same distance away when we look up. The reason for this is that we have limited depth perception. You can tell the relative distances to things, say, within a room, but if you get a few miles away, you lose that ability to judge relative depth. So if you look at the mountains in the distance, the peaks in the background might be several times farther away than the foothills, but all of them appear to be flattened together. The same thing is true for the sun, the moon, and the stars. The moon is fairly local. The sun is 400 times farther away than the moon, and the stars are literally trillions of times as far away as either one of these. And yet they all appear to share the same dome of the sky. Okay, let's look at the motions now if we were just to speed up the actual sky. What we see is the sun and the moon each circling the sky approximately parallel to this blue circle here. And this blue circle is the celestial equator. Notice that this line is the axis for the sky, the apparent sky. Up here is the north celestial pole. Whenever you spin a sphere, you're going to have 2 points that are fixed. So this is the north celestial pole, and that's the location of Polaris, or the North Star. Here's the south celestial pole. There doesn't happen to be a bright star nearby, but there's still the pole, the axis of rotation here. And so what we're seeing is the dominant movement is the spinning of the Earth. That happens once a day. The yellow line, or the yellow curve here, represents the path of the sun through the stars. And the sun moves along this curve, but it takes a year. And so I would have to spin this model 365 times for the sun to go once around this path. The moon is on this white curve, and that takes a month to go around. And so I'd have to spin this model about 29 or 30 times to get the moon to go all the way around. Let's pause this. Let's put the sun at a known point. It's going to be at the summer solstice. And let's put the moon at new moon. And let's let this come around here. So the way we have it right now, the sun and the moon are together in the sky. Remember that one is farther away than the other. But let's let this run for one day. Okay, notice the sun is no longer centered on this blue line. It's moved a little bit. It moves a little bit less than a degree per day. The moon, on the other hand, moves about 13 degrees per day. And so over the period of a week, it'll go a quarter of the way around the circle. So let's set the moon at first quarter. And so there it is, a quarter of the way around the circle. And notice from the point of view of our observer here, looking at the moon, the line of sight here is at right angles to the line of sight to the sun. And keeping in mind that the sun is actually hundreds of times farther away than is shown, the light from the sun would come in parallel to the way it's shown here. And so one half of the moon that we see, the right half, would be lit up and the left half would be dark. And left and right here is as seen by a northern hemisphere observer. So I'm displaying a northern hemisphere bias. If you're in Australia, it's backwards from that. But in any case, sticking with the northern hemisphere for now. The first quarter moon looks like half of the moon is visible, the right half, and the left half is dark. Let's go on to the next phase, which is full moon, which is where the moon is 180 degrees around from the sun. Here's the sun just after it's set, and here's the moon just after it's risen. So sunset and moonrise would occur at the same time if the moon is exactly full. Continuing on, if I go to the third quarter, let's let this run around. Notice now the moon is at right angles to the sun again, but it's the left side of the moon that would be lit up and the right side would be dark. And this is, by the way, notice at sunrise, the moon is still in the sky. So this is, the moon would be high overhead at dawn, and it would set at noon. So if we run it till moon set, you see that the sun is high overhead. Okay, and back again to new moon. Okay, now the way things are lined up right now, notice that the path of the sun and the moon cross at this point. This new moon would actually be a solar eclipse because you have a precise alignment. If I move the sun a little bit away from this place where the two orbits cross, notice that they are still in alignment, generally speaking. That would still be considered new moon, but you would not have an eclipse. So eclipses occur only on these two occasions when where the two orbital paths cross. We can approximate the moon's orbit with the sun's orbit, and let's do that for a minute, and then we'll come back to the full details afterwards. So if I just cancel out the tilt, I brought the two orbits into alignment, and let's look at a few things this way, and then we'll reintroduce this extra complication. Let's run it for a day just to separate the two bodies there. Okay, the purpose of this little exercise is to see how the motions of the sun and the moon would be observed at Serpent Mound. This is a site in southern Ohio built by an ancient Indian culture. And let's see what happens here with the rise and set times. I'm going to put the season here to summer solstice, and I'm going to put the phase of the moon to full, so the sun and the moon are opposite, and let's run it until we get to moonrise. Okay, here's the moon rising, here's the sun setting, and notice where the moon appears to be, namely right in this bend of the serpent's body, the southernmost bend of the serpent's body. And here's the path of the sun and moon as we've collapsed them together. And notice we have essentially perfect alignment with this bend of the serpent's body here. Let's move the season to vernal equinox, and let's again go till moonrise. And there we go. Here it lines up at the middle bend of the serpent's body. And let's go to winter solstice when the sun is furthest south, but the moon is opposite, remember, and so that's going to be furthest north. So winter solstice, and let's go to moonrise. And notice that if we line it up with this observer, it lines up over the midpoint of this arc over here. Okay. Now let's come back to summer solstice. We're going to focus on that one most of all. So I'm going to go to summer solstice, and that's when the moon should rise over here. And let's let it run. Okay. Now, what we want to do is reintroduce the fact that the moon's orbit is different from the sun's orbit, because this is not realistic. This is the ideal case. We could say that accounts for these 3 points here. Those points would be the rise points for the ideal full moon at summer solstice, winter solstice, and the 2 equinoxes. Let's put the tilt of the moon's orbit back into the picture. And so here's the moon's orbit. And notice that at this particular time, the moon's orbit and the ideal orbit, which is the ecliptic here, look pretty closely aligned. But let's step it a year at a time, and notice that if I change it a year at a time, it turns out that the direction of tilt of the moon's orbit varies, and where that orbit intersects the ground wobbles back and forth the full width of this bend of the serpent's body. Let's back up and see this in a different perspective here. So here is 1 year at a time. You can see that the moon's orbit is always tilted 5 degrees, roughly 5 degrees from the ecliptic, but which direction the tilt occurs is something that cycles, and it's an 18-year period, roughly 18.6, I believe. Let's go back in and see how this manifests itself. So if I take this to the max to the left here, this is the furthest north moonrise position. In fact, let's just run it around to moonrise. So this would be the minimum southern moonrise, if you can think of it that way. Some of the other diagrams for Serpent Mound speak in these terms. But this is the southernmost moonrise when the moon's orbit is tipped in this angle. And if I go to the other extreme, here is and then let's also go to moonrise. There we go. Here is the maximum southern moonrise. And notice how well that matches the width of this bend in the body. Okay. Let's step it a year at a time. So if I go from here 0, if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and here's 19. It's 18.6 actually would be the years to cycle in this way. So the moon's orbital tilt cycles around the ecliptic every 18.6 years. That variation in the tilt, by the way, that wobble, is called the precession of the moon's orbit. Okay. Let's see how this works out at the different seasons. If I take this to one of the equinox seasons, let's let the moon rise. There we go. Again, notice it's centered or approximately centered here. And if I go at 1 year intervals, you can see we're wobbling back and forth comparable to the width of that bend in the serpent. And let's go to winter solstice, and again go to moonrise. Okay, notice the yellow path goes here. Let's line it up with the base here of this figure. Okay, so the yellow lines up pretty well at the center here, if I just think of it from this point. So if I go at 1 year increments, the tip of the moon's orbit, again, varies pretty much within that arc. Okay, pretty good alignment there. So this was the first thing that caught my attention when I started this project. When I first met Constance, by the way, she said, "Can you calculate moon rises and alignments for Serpent Mound?" And I said, I don't think ancient cultures could do that sort of thing because the moon has such a complicated orbit. And it took me a while to wrap my head around it, but I realized finally that the moon in general does have a very complicated pattern of rise positions along the horizon, but if you focus only on the full moons, we have this simplicity that it's directly across from the sun, plus or minus a little margin of error. Let's let this run just to get an idea. If I take every moonrise instead of just the full moon rises, let's see what happens. I'm just going to sort of jump through these. I'm going to do a month's worth going down here and back. Let's see how this works. Notice that we still have the sun down here at close to winter solstice the whole time. And so here's our starting point. And notice, by the way, that the moon in this orientation of its orbit, in its precession, is out at a more extreme angle than the ecliptic itself. A day later, it still appears to be there. Okay, here we can see it's definitely making progress moving south. And again, we're still at very close to just a few days away from winter solstice. Okay, here we're down to the celestial equator. But again, the sun is still going to be setting at winter solstice. Let's show the whole movement this time. Here's the sun still down here just a few days later than winter solstice. But here's the moon rising further down. The reason for the non-alignment is we no longer have full moon. So here it comes further down. Okay, it's coming way down. Notice, by the way, that I'll just let it run here. The sun and the moon are closer together in the sky now. So this is going to be a thin crescent in the morning sky. It's past third quarter, approaching new moon. Remember we said it started out more to the north than the ecliptic, and here you see it's more to the south. Let's rotate it around so you can see it. So the curve over here is more to the south. So when you get a more extreme span from left to right, it's more extreme on the left and the right. And this is just the collection of all of the moon rises during a given month, just from one day to the next. Okay, so here's new moon, and the sun and the moon are rising together. You would never see this, but that's where you could predict it would be. And it's starting on the way back. I'm just going to let it go the rest of the way without commentary. Okay, notice the sun is approaching sunset at this moon rise, so we're approaching direct opposition here. Let's go one more time. Okay, it's just past sunset there. If I just looked at the full moons instead of all of the moons, what you would see is that it would take 3 months to come down to this point, and another 3 months to come to here, and 3 months here, and 3 months back. So you'd have the full moons in an independent cycle occurring once per year, just like each moon in a cycle that occurs once each month. So it's like a cycle within a cycle here. And if you look at the graphs in the accompanying article, both of these are illustrated. Let's move next to the sunset at summer solstice, which is another alignment found at Serpent Mound. But to do that, we're going to have to move our little figure up here to the head of the serpent. So here goes. There we are. So I've just moved our figure to this little V point in the head, and there's an alignment from here through the, and if you consider this to be an egg or whatever else this might be, this oval in front of the serpent's head, this alignment appears to be to the sunset at summer solstice. Let's see how that works out. I'm going to change the season to summer solstice, and I'm going to set it so it'll stop at sunset, and let's let it run. And there we go. Now let's see what this alignment looks like. And if I zoom in, there we are. And the alignment is close but not perfect. And we're ignoring the moon right now, so we don't even have to worry about the white one. But the sun itself, notice that as it's setting, it's a little bit to the right, a little bit to the north of this alignment. This is easier to see actually if we turn it around, look from the other direction. So here's sort of an artificial way. We're beyond the sky looking back at here. But notice here's the alignment, and at summer solstice, we're beyond the alignment. What we've shown elsewhere is that what this line appears to be pointing at is a place where the sun would be 2 weeks prior and 2 weeks after summer solstice. Okay. Now, this model is not a perfect sunset calculator because, first of all, this sun is an artificial size. It's not the size of the actual sun. Where the sun is at sunset is when the last gleam of sunlight is blinks out, and that would be considered typically to be the sunset point. There's been some messing around with that definition by other researchers because they're perplexed by this misalignment, and they're looking for possible explanations of why it's misaligned. So they thought, well, maybe they used other definitions. But if we stick with the traditional definition, when the sun blinks out is the most obvious, to me at least, that seems to be the most obvious event that you could record. It definitely is misaligned. And this is about a degree and a half. And so this point, it turns out, is about 2 weeks prior and 2 weeks after. This is an interesting offset, it turns out, because even though this might be the summer solstice, the moon might not be at full moon. We can artificially put this at full moon, so you can see where the full moon rises when the summer solstice sun is setting. But the moon could be in any phase at this particular solstice day. And so we might have to account for the moon being a little bit earlier or a little bit later when it gets to be full. So what we're looking for is the full moon closest to summer solstice. And so that is the issue here. If we align this 2 weeks prior to summer solstice, in other words, the sun is moving to the north, and then it turns around and goes back again. It crosses this line about 2 weeks before and 2 weeks after summer solstice. This alignment would mark out a span of time where we have about a month above this line. And sometime during that month, you're going to have a full moon. And so what you would do if you're using this as a calendar device would be to notice when the sun is in alignment with the head of the serpent, and that would mark the beginning of a month during which you would want to look for the next full moon. I'll leave it for you to read the article to get more detail here, but this is the observational component of what we take to be the interpretation of Serpent Mound and its usefulness to an ancient culture.